is on page 72. Okay, so we're going to be looking at rasterizing ellipses, and this is the last thing we're going to be doing with rasterizing lines. We're going to continue on to filling next week, and also we'll start on lighting. Okay, so we're starting to build up. Last term was all about how we construct the virtual world, how we define it. Okay, this term is more about, okay, once we define it, how do we actually show it on the screen? Okay, so this is rasterizing ellipses, and just to recap what we looked at on Monday, okay, we looked at drawing circles. One of the things we saw about circles is they have symmetry. Actually, I have infinite lines of symmetry, but we use 8-way symmetry. And so basically this means if I calculate a point on the circle in this first option, so starting at the 12 o'clock position, I only need to go around until y equals x, okay, to calculate this point here. If I know what x and y is, I can use symmetry to calculate points on 7 other options, so points on the circle. So if this is x, y, swap x and y around, I've got this point, negate x, I've got this point, etc. So once we've got x and y, we just have different combinations of x and y and x to give us our points on the other options. So we cut down our work significantly by doing so. Okay, and we looked at the midpoint algorithm, pretty much the same as Brescian's algorithm. We have an error. Okay, so for each time we've got to choose between 2 pixels, we have an error. If that error is positive, we choose 1 pixel. If the error is negative, we choose another pixel. In doing so, by having that error, we don't have to do any complicated calculations. We just calculate the error and we calculate the change in error. So if we pick 1 pixel, we change the error by a certain amount. If we pick the other pixel, we change it by a different amount. So we're still just checking for that error is greater than or less than 1. So given this diagram, very, very simple raster, okay, let's say this pixel here at x, y has been illuminated, and this is our idealized image. So this is the circle, or the arc, which is part of the circle, which we want to try and illuminate. So if this one's already been illuminated, step along one in the driving axis, which is x, okay, and we calculate the error between the idealized line and the midpoint between these 2 pixels. So this midpoint is at y minus a half. Okay, hence why it's given the name the midpoint algorithm. So we calculate this error. If it's positive, we illuminate 1 pixel. If it's negative, we illuminate the other. And we saw that if we use the Cartesian equation of the circle, we can derive an expression for the error. And if we calculate the change in errors, we have the initial error is 5/4 minus r. If we choose the pixel to the east, which would be this pixel, we update the error by adding 2x plus 3 to it. If we chose the pixel to the southeast, we update the error by adding 2x minus 2y plus 5. That's all very well and good, but we have that 5/4 calculation. We don't want any real numbers. We only want integer numbers. So what we can do is if we multiply all of these by 4, we get rid of that decimal, that fraction, and we've only got integers, which is what we want. Integer arithmetic much, much quicker than having to deal with decimal or real numbers. Okay, that's the midpoint algorithm, and we had a go at drawing circles. We get a decent circle. It's not ideal because we've got pixels. It's going to have a little sort of jaggedy edge, but it gives us the closest approximation we can handle. Okay, so that was the midpoint algorithm. What we're going to be looking at today is essentially the same thing, but we're going to be looking at ellipses. Okay, and this is an ellipse, pretty much a squashed circle, or an elongated circle, depending on what you have, depending on your radius. Actually, a circle is also a type of ellipse, just happens to be the radius in the horizontal direction and the vertical direction. So this is our ellipse. Okay. In this case, what I've done is I've called the radius in the horizontal direction A. So this is the distance from the center of the ellipse out along the horizontal line that goes through the centre. So what is that distance? I call it A. That's called the major radius. Okay, the other radius is the one going from the centre up the y direction, and I call that B. That's called the minor radius. So we normally call the larger of the two major, but in this case, I'm always assuming that the x radius is called major. What we have here is if we do if we have a look at the gradient along from a 12 o'clock position around the first, well, I'm going to call it octave, not really. Okay, this gradient here starts at 0. Okay, and as we go down here, we're decreasing our gradient, so it's becoming more and more negative. Okay, so remember, negative gradients like that. So it starts at 0 and it's become more and more negative. Now I've split this first quadrant here into two. I've called them region 1 and region 2. Region 1 is where the gradient m is greater than -1. Okay, so the largest value that n takes here is 0. The smallest value, let's say that's where the gradient is -1. Region 2 is where the gradient starts off at -1, goes all the way down, and eventually it's straight up, so that's infinity. The reason why, actually, can anybody tell me the reason why I split those into two? What happens when we try and draw steep straight lines? We have problems, don't we, when we try and draw steep straight lines, so we have to switch the driving axis. So in this case, in region 1, okay, this is the gradient of this line is fairly shallow. Okay, it's always greater than -1, so it's what we call a shallow gradient. So we use the x as the driving axis in this region. When we get to region 2, we have a steep line. So therefore we use y as the driving axis. So in this first quadrant, I'm going to use x as the driving axis up to this point, and then I'm going to switch and then use y as the driving axis to this point. We only have to concentrate on that first quadrant. We don't have to do the other three because we can use symmetry. We don't have as many lines of symmetry as circle line drawing, but we still got four-way symmetry. Okay, so we've got four-way symmetry. So what we can do is we only need to calculate pixels in the first quadrant. Okay, all the other quadrants are just combinations of x, y, x minus y, minus x, minus y, minus xy. So I'm not going to ask you to code this up for any of your assignments. So, I just put the code in so that you can say it's not something you'll need to do. But you can see very similar to the circle point, except we've only got 4. Okay, so we can't, with circle line drawing, we can have 8. So as soon as we know 1 pixel, we know 7 others. With ellipse symmetry, as soon as we know 1, we know 3 others. So we can't quite go as far as we did with circle line drawing. Okay, right, where is that boundary between region 1 and region 2? We need to calculate it. What we do is we use the Cartesian equation of an ellipse. So some people write the equation as x squared over a squared plus y squared over b squared equals 1. I prefer it. You multiply out through x squared, a squared and b squared, you get this form, Cartesian equation of an ellipse. Okay. X and y are just coordinates of a point on the ellipse. If we rearrange y, rearrange this to make y the subject, we get this. Okay, and what I've actually noticed this morning, I've actually missed out some things in the notes. So I think I'll sort of show you where we get this bottom one here. Right. So we need the boundary. So we need this point, and this is where the gradient is exactly equal to -1. So how do we find that? And the answer is calculus. Okay, so we have y equals b times. I'm going to actually write it using exponents over a. Okay, so that's our expression for y. I need to know where y, or the gradient of y, is equal to -1. from A level, ask an A level student to do that, they say, okay, you differentiate. So we're going to find dy dx. But if you see here, I'm going to write this in alternate form. Okay, as we see here, x is a function in a function. So therefore, what do? How do we differentiate a function in a function? Okay, not exactly. So if I let u equals a squared minus x squared, okay, therefore du dx is going to be minus 2x. Okay, so I'm using chain rule. So that means that y would be equal to a to the power minus 1 times b times u to the power a half. Okay, therefore dy du is equal to 1. So I've got a half times a to the power minus 1 times b times u to the power minus a half. Okay, we've got a couple of negative exponents there. So we'll have b on the top, we'll have 2 on the bottom, a on the bottom, and we'll have u to the power a half on the bottom. Okay, so we've got dy du equals du dx. So if we let u equals a squared minus x squared, du dx is minus 2x. Sorry if this is sort of teaching you to suck in, well, teaching your brain to suck in. It's always healthy to go back and revisit old things you haven't done in a while. Okay, so dy dx is dy du and du dx. Okay, so dy du is b 2a u to the power half, or u to the power half is just a squared minus x squared to the power half. Okay, and that's multiplied by du dx, which is minus 2x. So therefore we have minus bx over a squared minus x squared. Okay, so that's the gradient, that's m. So the gradient along our ellipse is given by this formula here. We need to know what the gradient, what the value of x is when y is minus 1. Okay, so all I do is, so when n is minus 1, okay, so we have minus 1 equals minus bx over a squared minus x squared power half. Okay, multiply both sides by minus 1, multiply both sides by the denominator. Okay, rearrange, make x a subject. Okay, so if I square both sides, all I've done there, square both sides, expand out the bracket, group the x squares together, okay, so you get down to x squared is equal to a to the power 4 over a squared plus b squared. Okay, but obviously we don't want x squared, we just want x. So therefore x is root both sides. And we get down to that. Okay, so there's a bit of calculus. That is, if you're wondering where I got the x equals a squared over root a squared plus b squared, that's where I got it from. So that's my x coordinate at the point where the gradient is equal to minus 1. And it's all in terms of the major and minor radius, or radii. So that's where the equation at the bottom of page 72 comes from. So I use x as a driving axis as long because that number there is less than y. As soon as it's greater than y, I then use y as the driving axis because I've got a steeper line. Right. Okay, so I'm just going to switch back to the slide. Right, so that's where I got that equation from. Okay, I'm not going to go through all of these calculations because it can get, I'm not going to go through them all again. I have given them to you in the notes. If you turn, back page 73, okay, what we do is exactly the same as what we did for the midpoint algorithm. Okay, essentially, this is on page 73. If we have, this is our error function. So this is the Cartesian equation of an ellipse. If I subtract a squared times b squared from both sides, I get some error function. So this is a function of x and y, and that will allow me to calculate how far away I am from the ellipse. And what we need is the initial error, okay, is the error at the 12 o'clock position, and you take that away from the error at the midpoint between the next two pixels. Okay, so 12 o'clock position is north b, because b is your radius in the y direction, okay, and you take that away from, if we add 1 to our x coordinate, because the x is the driving axis, and the midpoint between those two. Okay, so plug these into that formula, do a bit of rearranging, and we get there, that's, okay, so that's just expanded out. It cancels out to that. Okay, that's our initial error, and it's in the terms of the radii A and B. Now, like Brescian's algorithm and the midpoint algorithm, what we then do is we then need to calculate the change in error. Now, I called it here delta epsilon subscript, single uppercase I. So this is region 1. Okay, we're going to have a different change in error for region 2. Okay, so whenever you see a subscript I or double I, it means whether you're in region 1 or region 2. Okay, so the next pixel along. Okay, so this is the halfway point, the midpoint between the next two pixels. Okay, again we use this function here. Okay, and we get this expression, and we do it for the one in the pixel after that. Okay, that's the next pixel. That's the pixel after that. Why I plus 1? We don't know what that is. Okay, when we go to this pixel, we make a choice, but I don't know what that choice is. So I've labeled it yi plus 1. Okay, so very similar. Okay. Plug them in, find their difference. So this is the one in 2 pixels time minus the one in 1 pixel time. This is just, it looks rather ghastly, but it's just multiplying out those brackets. Okay, and we get to this horrible sort of big, nasty sort of algebraic function there. That cancels out quite significantly. If we cancel out, simplify, collect like terms, done a bit of factorization, and we get this. Okay, so you notice this is our change in error, and we still have that unknown yi plus 1 value. So that yi plus 1 value is whether we went to the east pixel or whether we went to the southeast pixel. If we went to the east pixel, yi plus 1 is simply yi. Okay, and our change in error becomes this. If, however, we went to the southeast pixel, our yi plus 1 is now yi minus 1. Okay, so our next value of yi would be decremented by 1. So if that's the case, you end up with this. So these two expressions are the change in errors depending on what pixel we went to. Okay, and then lots of, you can follow it if you want. You can get a scrap pen and paper and do it tonight if you want, rather than going out. Why not do some of this? Okay, but that's where it comes from. So essentially it's the same as midpoint algorithm, but just for ellipses. And that's what I've just gone through. So I called it the change in error for region 1 if we went to the east pixel, change in error for region 1 if we went to the southeast pixel. Okay, that's all well and good. What about region 2? Now in region 2 we have a steep line. And we saw from our work with straight lines last week, we need to switch to the y being the driving axis when we've got a steep line. So this is what we got. This is the problem. We have this idealized line here. Okay, all along here we've got a gradient less than -1. Okay, so we're going to now switch to the y being the driving axis. So instead of going across in x, we're now going down in y. And what we do is we calculate the midpoint horizontally. Okay, so we calculate the midpoint for xi plus a half. Okay, so we're assuming this pixel here has been illuminated. We choose between the south pixel or the southeast pixel. So we make a choice between these two. So essentially what you're doing is midpoint algorithm, but now with the y-axis using as the driving axis. Okay, the change in error in region 2, calculated exactly the same way. It's going to have different expressions, but using exactly the same method, comes out as this. Okay, so notice instead of yi plus 1, now we've got xi plus 1. So we don't know whether we went down to the south or to the southeast pixel. If the pixel to the south was chosen, xi plus 1 is simply xi, and we have this as our change in error. If the pixel to the southeast was chosen, we add 1 to x. And doing a bit of algebra, a bit of simplification, we get this as our error. Okay, so essentially you do the same thing, except for we have different changes in errors. These are all integer-only expressions. Okay, so these are, we initialize the error for region 1 as being this, and we change the errors accordingly. When we get to region 2, our new initialized error is our error for region 1 with this applied, and then we change the errors there. So it is more complicated, but these are only integers. We're not messing about with real numbers anywhere. And that's the output. That's what you get. So I've given you some code. I've given you some flow diagrams in the notes. But to cut a long story short, this is what you get from the output. So what I've done here is sort of done concentric ellipses, and what I've squashed the minor and major axes. So you can see, like the circle I'm drawing, we have a fairly good representation of the ellipse. Okay, we've got the jagged edge. That's unavoidable with pixels. But it allows us to actually draw curves which aren't always circle arcs. Okay? Quite often you don't want curves which are circle arcs. If you want to design a car, you don't always want them to be circular like bubble clouds. You want them to be have a nice smooth line. Okay, so that's what we use. We use a midpoint ellipse algorithm. Okay, we've got about 15 minutes left, so I'll line up one of my activities. Before I do that, is there any,